recording started. Okay. Okay, so today I thought that I could do a bit of a follow-up on the unification with sigma types. So the last week, when I told you about unification with sigma types, I was essentially kind of just repeating what I remembered about how the Agda sigma unification works, and also this higher order unification paper that I mentioned. But since the last session, I've been thinking about what is the best way to do this, and now I'm pretty sure that this is actually not the best way to do it, and instead I try to work out some kind of some better solutions. So I looked at this paper again, and I also looked at the Agda source code, and I investigated what is actually happening in Agda. And if you remember the last session, I mentioned that the point of unification with sigma is that whenever I have a problem like in gamma, I want to unify some, let's call the meta variables alpha now. I mean, in the implementations in elaboration zoo, I call them a question mark something, but let's use Greek letters instead now. They look a bit nicer. It's just that in the implementation it is way more easier to get enough numbers to display everything, because usually we get way more meta variables than Greek letters. So that's why I call them with numbers in the implementations. But here we can use Greek letters, and that's what people usually use in papers and formalizations as well. Okay, so let's use this alpha for a meta variable, and then the problem is that alpha is substituted some spine, then we want to unify it some arrays. And now this is a bit of a simplification, because I say that alpha is not a closed function, but rather alpha is a contextual meta variable, so alpha lives in some delta context. So now this is the situation. So we have alpha in delta, which has type A, and then we want to solve this problem. And then we also know that arrays has type A SP in gamma, and we also know that SP is a substitution from gamma to delta. So we know this, and previously, so what's the solution, or what's a solution to unification with sigma types? So then the solution was that we had two isomorphisms which are definitional. So we have definitional isomorphisms. One is the axiom of choice, or columnization, which is that if you have a function which returns in a sigma, so if we have an AA which returns in a BB times, so BA times CAB, then this is isomorphic to having a function which goes from AA to BA together with a function which goes from AA to C of ABA. So this is kind of this columnization where we want to lift, we have something which returns a sigma, but then we want to lift this sigma out. And if we repeatedly do this columnization, then every sigma moves out to the top level, but in the top level we can just use the meta context to represent a top level sigma as multiple meta entries. So that's why we can convert every nested sigma into a top level new meta variable. So we have this axiom of choice, and we also have currying, which is that if I have a function which goes from a sigma, so if I have a function which goes from an AABA to some C of AB, then it's the same thing as having a function which goes from AA to BA to C of AB. So we can use currying to remove sigmas from function arguments, and we can use axiom of choice to remove sigmas from function results. So if we use both of these, then we can, in principle, remove every sigma and convert them into top-level sigmas.
Question: why do you call this axiom of choice? How does the name come?
The name comes from the homotopy type theory book, and I'm not sure what is the original naming, or what was the original inventor of this naming. But I think probably even before the hot book, it was called the type theoretic axiom of choice. I don't know why. It looks a bit like the usual axiom of choice, because here we have, because what happens here, so usually, in set theory, the axiom of choice is used to get a function which performs this choice, and without the axiom of choice we do not get a function. And here it looks a bit like the axiom of choice in set theory, because here we have a family of these kind of sets, and we know that at every A it's inhabited, and from this we can conclude that there is a choice function which is this function, right? So the choice function can actually pick out for every A an element of B. I'm not sure what's the best explanation, but this is kind of just a folklore naming for this isomorphism.
Okay, then I guess I can look up the code book, see more details.
Yeah, there might be some explanation in the hot book as well. So you have this, and then, so nice property of a definitional isomorphism is that, so the definitional isomorphism, just to do a bit of a refreshing, so a definitional iso is like a function from A to B, and then a function from B to A, such that fg is by definition ID, and gf is by definition ID. And in unification, so now we want to solve unification problems, and unification problems, we want them to be unique up to definitional equality. So we can only use definitional isomorphisms to simplify problems, because this preserves uniqueness up to definitional equality. So we cannot use any isomorphism which is only propositionally provable but which is not definitional here. And we can use it, and then we just say that instead of solving this problem, we just convert A to A prime. And okay, so another thing which I should mention is that currying can be also used in context. So, and this is also important, and I forgot to talk about this, and I didn't implement it, but we can look at some examples for why this is also important. So this context screening just says that if I have a gamma extended with a sigma, the context itself is isomorphic to the twice extended context. And an isomorphism of context is just a pair of substitutions. So I can do a kind of a curry-uncurry substitution.
I can't use that.
There are some microphone issues. Okay, I muted Molikto, so if the microphone is solved, then please tell me to unmute, but I think you can unmute as well.
You have probably just muted him personally, so everyone has to mute him personally, or you have to apply server-wide mute somehow. I don't know how it exactly works.
No, I actually so just now I clicked on mute for Molikto.
Yes, but that only applies to you.
Oh.
I can still hear him, but I can still right-click and mute, just telling the others that they should probably do this until the issue is sorted out.
Oh, okay. So the way it works is that everyone has to mute for themselves.
I think that you, as the server creator, actually has the right to mute him server-wide, but I don't currently know how.
Oh, okay, I see now. So there is two. I have a server mute option, and I also have just a personal mute.
Yes.
Okay, I clicked on the server mute, but now it's not very noisy, just a little bit. But
I still think you should apply the server mute.
Okay. Okay, so let's continue. So I was talking about this context currying. So in context currying, if we have a sigma in a context, we can convert it into a twice extended context. So I can have an A and then a B in B of A. And then the higher order unification paper. So what the higher order unification paper does is that whenever I have a problem which consists of all of these stuff, we can instead just do this kind of sigma eliminate A into an A prime, and also sigma eliminate gamma to gamma prime, and we can also do delta to delta prime. And then we get a new problem, and the new problem looks like in gamma prime we want to solve alpha. And then we also have an SP prime, because we have to transport everything along these isomorphisms. So we have an SP prime and some arrays prime. And actually the way it works is that because we are converting top level sigmas into multiple meta variables, then what we have is some number of new meta variables. So So sigma is removed from everywhere, and top level sigma is converted to multiple alpha I. So this is the idea, but last time I mentioned that I only implemented currying but not the axiom of choice, and I also didn't implement this currying in local context. So I looked at what is actually implemented in Agda. So it turned out that in Agda we have like currying. So we have 2 and 3, but we don't have axiom of choice even in Agda. And probably for a related problem. So my experience was that axiom of choice is quite expensive and also quite complicated to implement. So it turns out that although in the paper there is this axiom of choice, in the actual Agda it is not implemented. So but let's look at some examples. So some examples. I mean, last time we looked at some examples, but I think that was a bit insufficient. So there are more interesting examples. So for example, what if I have alpha applied to x.1 and I want to unify this with anything? For example, maybe bool. And here this projection binds stronger than function application, so I have this alpha, x.1, and in the context I have that x is a variable with a sigma type. So I have that in the context x is a variable with a sigma type, or we can alternatively also represent it by saying that the context consists of some prefix, and then we have this, and then we have some gamma 1, and then in this context x is still a valid variable. Okay, and how can we solve this? And here we have to use the context currying. So we have to curry gamma, and we have to say that instead of this context we want to have the curried version. So we have a gamma 0, and then we have an x0 has type A, x1 has type B of x0, and then we have gamma 1. So then we have a new curried context. And of course we also need to have a substitution, like a substitution which witnesses this currying isomorphism. So substitution witnessing the currying iso, and now we have to transport everything in the unification problem using this currying isomorphism. But after we do this, what we get is that x.1, so x becomes substituted to x.1, x.2. So there is this eta expansion of x, and then the problem becomes alpha. I'm sorry, so not x.1, but here we have, maybe this is a bit confusing, let's call it x1, and so let's call it x1 and x2 for the first projection and second projection, but now these are not projections, these are actually just variables in the new context. So in the old context we had a bound var x, and in the new context we have two bound vars x1 and x2. And if we perform this currying substitution, then what we get is that alpha x1 equals bool And then the usual solution for this is that alpha is solved to be lambda x1 dot bool. And then this is a pattern problem. But so this is not a pattern problem, but after we do an eta expansion of a bound variable, we get a pattern problem. And this works in Agda, as I mentioned. Okay, so maybe let's call this the first example for context currying. And let's do an example also for currying for eta expansion of the meta. Eta expansion of alpha. So this eta expansion of alpha is actually kind of it's a special case for using some combination of axiom of choice and currying on the meta variable alpha, and so it's kind of a mix of curry and AC. So I think I was a bit wrong, because Agda has this eta expansion of meta variables, and it can be conceptually understood as some mix of currying and AC, but only in the return type of alpha. So it's still the case that there is some kind of limited axiom of choice in Agda as well, because it's possible to do it, but only in the return type of alpha, but not in the argument of alpha. And then what happens is that I have some alpha. Okay, so very, very simple is that alpha dot 1 equals bool. And then alpha dot 1, so it's a meta variable with a sigma type. And then the solution is to convert. So here we have a top level. So this is a top level sigma type in the type of alpha, and then we can convert it to, we can eta expand it to a pair of meta variables. So we expand to pair of metas. And then we have an alpha one which has type A, and we have an alpha 2 which has type B of alpha 1. And then we can go from this problem to this problem. And we can immediately solve to bool. Okay, so we can view it as kind of an axiom of choice, because we are, or we can also view it as a kind of currying, because we have a sigma in the meta context, but we can convert it to twice extended meta context. So sigma meta context becomes twice extended meta context. Okay, let's do another eta expansion. By the way, I unmuted Molikto, and now I think we do not have noise, so if it works, then then okay. Okay, so let's look at another example for eta expansion, but now we have a meta, which is a function which returns a sigma. So we have an AA. Maybe. So let's just return in some BB and then CB. And then we can have the problem where we have alpha. Okay, Gabor noticed some typos. So on line 53, one should be just alpha. So line 53, one should be I don't really understand the line 53 complaint. Oh, yeah. Okay, I understand. Yeah, alpha has this type. Sorry, and thank you. And on line 44, so we have x1a and b x0. Here this is x1, but otherwise I think this is fine. But you so I think this 44 is now fine. We have gamma 0, x1 in A, x2 in B of x1. So let's do this other example for eta expansion, but now we have a meta, which is a function returning a sigma. So now we can have a problem like alpha x, and then alpha x is projected. Like alpha x dot 1 is something. So alpha x dot 1 has type B, so here we just have to write something which has type B, but maybe let's just write bool here. And then B is the universe. Okay, and now if we do an expansion, then we get that instead of alpha, we have alpha 1, which goes from A to B, and then we have alpha 2, which goes from A to C of alpha 1, A. And then the problem becomes, so here we have alpha and we apply alpha to x and then take the first projection, but this actually means, so we have this expansion, but then we also have this substitution. So alpha is actually solved, and the way it is solved is that it's a lambda A and then alpha 1 A and beta, sorry, alpha 2 A. And if you apply this solution, then this problem becomes, so we can kind of copy this and then apply this to x and then take the first projection and we can simplify it to alpha 1 x. And from this we get the solution.
So is this a special case of the axiom of choice?
So now, yes. So here what we do is that we use axiom of choice to convert this into a sigma of functions, And then we use meta context currying to convert it into a pair of meta variables. So the way it works is that convert alpha type with AC and then curry meta context.
Does Agda solve this or not?
Yes. So Agda supports currying in local context and meta context. And this kind of currying, I mean currying in general, so it can curry the type of the meta. So we will see an example for that shortly. And it can do the axiom of choice, but only in the return type of the meta. It cannot do an axiom of choice conversion in an argument of the meta. But we will see examples for everything. So what is an example for so this was like eta expansion, which is kind of a mix of currying and axiom of choice, but in the we can only use the axiom of choice in the return type of the meta. That's why we can eliminate these projections from problems. But we can also have a problem like this. So I have an alpha which is applied to a pair. So in this case, alpha has some sigma type. Let's just write for simplicity just a pair type. So maybe alpha goes from A product B to A. And then we have this problem. And then here the solution is just we can curry alpha by removing the sigma from the argument of alpha. So we have kind of an alpha prime, which is type A, B, A, and the old alpha is solved to be just a curve, just to be lambda A, B, and then sorry. So the old alpha has this type, so it has to be like lambda A, B, and then alpha prime A dot 1, A, B dot 1, A, B dot 2. And then this becomes just alpha prime X, Y, X, and can be solved as like this. So this is currying a meta argument. And this also works in Agda. Okay, so what is still missing? Okay, so now let's do an axiom of choice in a meta argument. So AC in meta argument, and then the problem looks like this. So I have an alpha, and the alpha could be applied to a lambda x dot fx first projection. And then this equals to something, maybe bool. And here, so f is a bound variable, and in gamma, f has type. So f is a function which returns a product. And you can see that here I apply f to this x, which is a product, and then I do a projection. I'm sorry, I think I'm giving the wrong example here. So this is AC in local context, right? Because now I have this in the local context, and I want to somehow transform the local context to remove this projection from the inside of this. Okay, so what I do is that I have F1 and F2, and F1 goes from A to B, and F2 goes from A to C. And I have a new gamma. So now in gamma prime, I have these two functions, and I have to do this substitution from the. So I have to do the substitution, and then f is substituted to the lambda x dot f1x f2x. And now the problem becomes alpha and lambda x dot, but fx dot 1 is just definitionally the same as f1x, and now I have to unify it with bool. But here you can see that that this is eta convertible to just f1. So I can do an eta reduction, and then I get alpha f1 bool, and this means that I can do the usual pattern solution. So here I can do the usual pattern solution because this is just a normal bound variable in the transform local scope. So this is this axiom of choice in local context, and this is already something which is not supported by Agda. And we can also do an AC in meta argument type. So let's try to do an example for that. So I can have a meta which has as an argument a function which goes from B to C and then returns some D. And then my problem can be like lambda x dot, and here I can also have like y and z, which are bound variables in the scope. So y would have type B, and then z would have type C. Would this be okay? No, I don't think this would be okay. So I have two functions. So I have an fx and I have a gx. So I really need to have two functions in the scope for this to work out nicely. So I have an f which goes from A to B, and I also have a g which goes from A to C. And then, if you look at this, I have alpha, and to alpha I give a function like this, and it seems to be well typed, and then I want to unify this with, for example, whatever. I mean, this right-hand side in all of these examples is just whatever, because I only care about trying to convert this alpha spine into just some pattern of variables. Okay, and now I can transform alpha, so I get a new alpha prime. And the alpha prime has type A arrow B. And this is actually, it's a combination of AC and currying. So I can do an AC, maybe it makes sense to split these two steps up. So if I do an AC, then I get an A arrow B product A arrow C arrow D, and then if I do query, then I get an alpha prime A arrow B arrow A arrow C arrow D. And if we do this kind of substitution, then the unification problems becomes lambda x dot fx lambda x dot gx equals bool. And then we can do an eta reduction, and then we get alpha prime f g bool, and then this is just a pattern problem. Okay, and so these two things, they don't work in Agda, but these are in the higher order unification paper. And now I can talk a bit about why this is a bit problematic. I mean, there are problems with efficiency, but it's not the best that we can do. So I think that these three are not all the isomorphisms which you can actually use, because there is also the flipping. So A, B, C is isomorphic to B, A, C. So there is also this flipping, and it's not supported. It's not supported even in this paper. So I think there are two main improvements to this. So one is performance. So here the problem is that we are doing all of these kind of expansions, but we are generating like lots of new metas. So the problem is like we have to generate lots of new metas, and we have to compute all the types, all the new types of new metas, and we have to transport everything along isos between all the new meta types. And we also have to compute a bunch of types, create a bunch of new metas, transport everything along the isomorphisms, and also this is not immediately obvious how to minimize the amount of work. So we can try to do in a kind of a syntax directed way, but I cannot give you a good intuition, but I mean, we already have a problem when we want to implement the axiom of choice in an efficient way. So I talked about it last week, and yeah, so it's just the start of the problems, and it's not obvious to me how to do the minimal amount of work which is required to solve one particular problem. Okay, and another problem is that we have to do eta reduction. So here we have these examples, and this is supported by Agda. So eta reduction in patterns is supported in Agda as well. Yeah. I mean, these 5 and 6, they are not supported, but in general, eta reduction is really supported in Agda. But then eta reduction is just not efficient, right? So if you want to do eta reduction in the presence of sigma types, then it's not efficient. Because then we have to do like a t.1, and then the t.2 should be reduced to just t, but this requires checking the conversion of so we have to do kind of a general purpose definitional equality checking to check that this thing on the left hand side is of the right shape. This requires conversion checking. So eta reduction is not that bad if we only have function types. So if we have function types, then the rule is that lambda x dot fx reduces to f if x is not free in f, but this can be done in linear time by basically doing two passes over terms. So on the first pass I am annotating like variable occurrences and strengthenings, and on the second pass I just do an eta reduction. So this can be done. Fine, but with eta it becomes a bit more expensive. I mean, usually it's not super expensive because whenever we have these patterns, so in these unification problems, these patterns are usually not too big, but it's still a bit ugly that we have to do this sigma eta reduction. Okay, and then the other thing is that flipping is not supported. Let's just call inside problems with above solution. Okay, so flipping is not supported, and then I can give an example for a unification problem which requires transporting over flip. So I can have some alpha and then lambda x dot y fyx, and in gamma I can have an f which goes from A to B to C, and then I want to unify this with anything, and this is solvable if I say that f prime should be BAC and f should be substituted to just flip of f, and then the problem becomes alpha lambda x y dot flip of f prime x y, so that we can solve it like this.
But does this mean that you can have also like more complicated permutation and then rules for more complicated?
Exactly. So if we
not really something which scales.
So if we have if the flip isomorphism is generally supported, so we say that we have like a full solution which modulo flipping, then we can do arbitrary permutation because we can just use flipping multiple times. So this is like not just simple flipping, but potentially permuted arguments anywhere. So arguments basically can be permuted in any function in local scope, but should be also permuted in the type of a meta. But that's not very relevant because so this kind of pattern unification does not really depend on the order of the arguments to a meta, but it can actually depend on the order of the arguments to a function which comes from the local scope. So
not completely clear to me if that you also drop some argument, so it would be lambda x by z.
We cannot drop. We cannot drop because that's not a definitional isomorphism. So So every transformation which we can do must be just a definitional isomorphism. So we cannot gain or lose any kind of information.
I mean, if you have a unification problem like line 142, that's a problem, yeah? You can have lambda xyz.
Yes, and so and what else? So lambda xyz.
And just the rest.
You mean this?
This is a problem.
Oh yeah.
I'm not sure if it should be solvable or not, but
It's not solvable because I mean we can just try to do this flipping transformation, and then we have lambda xyz dot f prime xy, but it doesn't help, right? Because this cannot be eta contracted because this gets in the way. So
yeah, but one solution is just ignore this z argument. Or maybe I'm confused here.
so what we want to solve is alpha,
Yeah. Sorry.
and it's kind of so the thing which we have it doesn't make sense to talk about ignoring z because we want to solve alpha. But it's easy to see in general that if we have an alpha which goes from which takes a function as an argument, and then we want to have a unification problem which has a constant function here. Then this doesn't have a unique solution, so this can have multiple solutions, because we can only know what happens. We only know the behavior of alpha if we give it a constant function, but not all functions are constant, so we do not know the behavior of alpha on every argument.
Okay, yeah. That's a bit confusing.
Okay, so now let's solve all of these problems. And so preliminarily, so I have something which all solves all of this. So I have solution for all of above issues, but I have not yet implemented it. So I started to formalize it on paper. And if you're curious, then I can also talk about what seems to be a good way to formalize these unification problems in a categorical way. So not imp yet, partially formalized using CWF categorical stuff. But what I do not have yet the solution. So this solution works for all of these kind of pattern unification problems in a nice way, but pruning is I haven't yet worked on how to do pruning. So to do pruning using this solution. And also like handling nonlinear spines. Okay, but actually I remember now that I should also give some example for pruning using this. And probably I should do this before the problems. Okay, so this is another thing, like this is an extra example. So how can we do pruning with this kind of sigma elimination? So previously there was like for example, so pruning is about solving methods with functions which are constant in some of the arguments. So pruning is about dropping dependencies of meta variables. And one example for pruning is when I have that alpha x should be equal to maybe bool arrow. So this is a function type, so this should be equal to bool arrow beta of xy. And here x and y are boundwards in gamma. And here the problem is that the right hand side not only depends on x, but it also depends on y. So then the pruning is kind of removing y dependency from beta. So we say that this problem is only solvable if b does not actually depend on y. And so we can act on this. So we say that if b has type abc, or maybe ab set, because this should be a type, then we have a b prime which only goes from a to z. And then we solve beta to be lambda ab dot b prime of a. Okay, and now we have this transformation of the problem again. So problem becomes this. And now this is solvable. So now I can just do the usual thing. Okay, so here we have this pruning, and but here we have to check that this solution is well typed. So we have to check in general that the pruned solutions are well typed. Because if this function is a dependent function, so for example, what happens if the return type of beta depends on the value of this argument? Then generally it means that this is just not a well-typed thing. So additionally we have to check that after we are pruning everything from the type, then it's still well-formed. Okay, so this is an example that probably we've already seen. And what happens if I have some projections or some pairings in something which I want to prune? So I can also have some sigma in pruning. I can have an alpha x, and I try to unify it with bool arrow beta. Okay, sorry, there was a bit of an interruption. So for example, what if I have this? And now I want to prune only the second projection of the first argument from beta. And then the solution here is just the same as with pattern unification. So I just want to eliminate sigmas from beta. And once again I get this. I get some beta. First I get the beta prime xy after I eliminate, after I do this currying on beta, and then I get the bool arrow beta prime x after doing, so this is a currying, and then This is after pruning. So the idea is the same, and here it's also possible that we have to use any kind of way to eliminate CPaths. So here we had to use currying, but we can also have projections here. We can also have whatever here, and we have to use the same method. Okay, and this is what I have not yet figured out in the new solution. But let's give some intuition for the new solution, or some kind of history of what I tried to do. So first I looked at, so there was a suggestion by Olaf. So like pattern unification with extended patterns or something like this. And this is kind of try to handle, so handling product types directly. So this is a paper about handling product types directly without having to transform everything along these isomorphisms. But okay, so let's try to do some examples of what happens if I have an alpha of xy equals x. Then this Duggan unification, what it will do is that it can directly solve this problem to be lambda xy dot 1. Okay, or another thing is that if I have an alpha of x dot 1 equals x dot 1, then this unification algorithm can directly solve this to be just lambda xx. Okay, but then I haven't looked at it like very carefully. I only kind of skimmed it, but it seems a bit ugly. And the source of the ugliness is that now I have to treat these projected expressions as some kind of primitive things. So projected expressions in this Duggan are treated, become kind of primitive. And then I also have to handle kind of mappings from projected expressions to projected expressions, and as some kind of generalized substitutions, and it becomes a bit messy and ugly in my opinion. And this still doesn't do anything with flipping. And I haven't checked, but I think that this also does not work with axiom of choice. So it can do a direct solution only modulo this currying, or maybe the axiom of choice only in the Agda limited kind of way. Okay, so the idea is that I have some alpha, and alpha is applied to t1, t2 dot ti, and I want to unify this with arrays. And this is the problem. This is the problem, and we also know that in delta alpha has type A, and we also know that if we are kind of bunching together all of these arguments and just make a substitution from it, then that goes from gamma to, so if I have t1 t2 dot ti, then it's a substitution which goes from gamma to delta, because in this context I have to give all the delta, like a delta worth of arguments here. So that's why it's a substitution from gamma to delta. Okay, but now if we are looking at the eventual solution, so if there is a solution, then it always looks like alpha should be the same as lambda. And if we have De Broglie levels, then this is just null, this is just 0, 1, 2, I, and dot. And here we have arrays, which is substituted with an inverse kind of substitution. So there is some sp minus 1, which I have to use. So I mentioned before that we can view pattern unification as a way of inverting the spine substitution. So previously, if I have an SP which goes from sub gamma delta, then the pattern unification, like the main problem of pattern unification is how can we invert an SP to get a substitution from delta to gamma. Okay, so every solution looks like this, and if you look at this spine, then it looks like an identity substitution from delta to delta. So if we write out this using De Broglie levels, then this is nothing but the identity substitution from delta to delta. So here I'm not giving the formal account of this solution, but kind of just try to give some intuition. And because De Broglie levels are not very readable, then it also makes sense. So it can be for illustration purposes. It's nice if we say that we name these variables starting from A. So we have A, B, C, something. Dot array just sp minus 1. So for illustration purposes, it helps a lot that we are naming the arguments of the meta solution starting from A, but we are naming the the local variables in gamma starting from X. So we have x, y, z, or maybe f and g. So we say that x, y, z, f, g are the vars in gamma. And we say that a, b, c, d are kind of the eventual arguments, or we can also view them as the vars in delta, right? Because if we are solving alpha, so if we have this lambda expression, then the type of that would be something which goes from a delta telescope of arguments to some A type. And then the telescope can be viewed as A, B, B, C, C, dot, 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 and then we are returning in some result type. Okay, and now the solution is that whenever I have an alpha of T1, T2, Ti equals arrays, then I know that T1 should be A and T2 should be B, and so on and so on. So what I can do is just unify in scare code. So I unify T1 with A and unify T2 with B, and so on. So I'm basically unifying this spine. So unifying SP but this should be also in square quotes. So I'm unifying the spine with the identity substitution. Substitution ID, which goes from delta to delta. Of course, this is not well typed, right? Because SP goes from gamma to delta, and this identity substitution goes from delta to delta. But if we are talking about partial substitutions, then it can be made formal in a well typed way. Okay, but let's just do a bunch of examples. Okay, so I'm just a bit more explanation here. So I unify T1 with A, I unify T2 with B, and all of this, it returns a partial substitution from delta to gamma. So all of these unifications compute some partial substitution from delta to gamma, which means that gamma variables are mapped to some delta variables, and after I finish doing each of these kind of unification things, then I can combine all of the resulting partial substitutions together. But let's see some examples. So merge all partial substitutions. Okay, so let's do a quick example. If I have alpha xy equals x, then here what happens is that I have AB, so I know that if the solution to alpha will look like lambda AB dot something. So I do this unification, so I unify x with A, and then I get this partial substitution, which maps x to A. So this is a partial substitution because it maps this variable to A, but it doesn't map anything to anything else to anything. So this is undefined on everything else. So this maps x and undefined on every other variable. But if you think back, this is very similar to how we actually implemented in elaboration zoo the inversion of a substitution. So we are kind of building up a partial substitution whenever we see any new argument in the spine. And this is just the generalization of the implementation which we already had. But the generalization is that now these terms can be much more general than before. They don't have to be patterns. But instead we have this slightly more general kind of term inversion, which you can use as some kind of unification. And then this term inversion gives us partial substitutions on every argument. So we have this. So we have to unify x with A, and then we have to unify y with B. And then we get y b. So the resulting substitution is something which goes from x to A, y to B, and then we apply. So this would be like the inverted substitution from the spine, and I can just use this on the right hand side. So if I substitute the LHS with SP minus 1, then it's x with this substitution, which is just A, so therefore the solution is alpha lambda AB dot A. So this actually it doesn't differ from the elaboration zoo implementation in any interesting way. But then we can make this a bit more general. But before making it a bit more general, Let's just look at so this is a basic example, basic pattern. Before going a bit further, let's also look at a nonlinear spine. So I have alpha x x. I want to unify it with x. And now I have a here and b here. So the x unification with a, it returns the mapping from x to a. But then again I have an x unification, but now with b, so this returns an x mapped to b. So here I have a problem because these two partial substitutions cannot be merged in any natural way. So this cannot be merged with this. And why? Because they are both partial substitution, but they disagree on the value of x. So whenever I have two partial substitutions, I can merge them. I just so let's look at an example for merging partial subs. So for example, I can have something like x is mapped to true, which is a substitution going from maybe x bool. Okay, so this is a substitution which goes from the empty context to x bool, right? Sorry, x bool and y bool. So a total substitution would have two entries because it has to map x to something and it also has to map y to something. But this is a partial substitution because it only maps x. And then likewise I can have a mapping of y to false. And let's call it p sub for partial substitution. And now I can take, so there is actually categorical product of these two. And I can call it using the product sign. And in this case it's just defined to be x mapped to true and y mapped to true as well. Okay, and why is this a categorical product of these two partial substitutions? And so the reason is that if I have like a p sub from gamma to delta, so this is the set of partial substitutions from gamma to delta, but this is partially ordered by definedness. So one partial substitution can be more defined than another partial substitution. And if I have these two partial substitutions, then because they do not disagree on anything, so two partial substitutions which do not disagree with, on any mapping can be merged together to a partial substitution which is more defined than either of these two constituent partial substitutions. So this is kind of the least upper bound with respect to definedness, so that's why you can think about it as the product of two partial substitutions. But if there is some disagreement, so if x is mapped to true, but x is also mapped to false, then it is not true anymore that such product exists, and that's why we get this linearity error. But this is just kind of a short categorical excursion. So I worked quite a bit about formalizing this whole unification algorithm with using these categorical terms. I could talk about it, but maybe not today because we don't have that much time left. Okay, so this is an example for nonlinear spine, and I say that the reason that this spine does not work in the algorithm because there is no categorical product of these two partial substitutions, and if we want to prove the correctness, then we have to use the property of the categorical product of substitutions, and otherwise we do not get any unique solution anymore, and it's kind of a more abstract explanation for the problem that this can be solved in two different ways. Okay, but let's also look at an eta conversion example. So this is something which is pretty inefficient in Agda, because in Agda we have to do very explicit eta reduction, because Agda wants to eta reduce everything into a pattern form, but we do not have to eta reduce anymore, and we can just handle it in a very efficient way. Okay, so let's do like this. And Agda would need to do an eta reduction here, but our algorithm has to just do this unification of this thing to A, and A is the first argument of the solution, or the first variable in data. Yeah. Okay, so now we do lambda x fx A. And here we can just reuse the usual techniques from unification. So we can just say that for all x, I have to solve fx equals ax. So we are just introducing x as an extra bound variable in the local context. So both on the left side and on the right side, but we have different contexts on the left side and the right hand side. So if the LHS lives in gamma and the RHS lives in delta, but it's not a problem to just do a context extension on both sides of this thing. So that's why I use unification in scare quotes, because this is not a homogeneous problem, because the left hand side is something in gamma and the right hand side is something which lives in delta. So it's a bit of a heterogeneous variant of the usual unification algorithm. Okay, so now we have to solve this, and how do we solve it? By using pattern unification, right? So now we have this problem, but this has the solution like this. So what we are returning here is f is mapped to lambda x dot ax. Okay, and then this is the inversion of the spine. So now the solution becomes lambda a dot, and then we apply this inverted substitution to f, lambda x ax. Okay. And now it works nicely. And the nice thing is that this also works if we have sigma types, and it's also just effectively linear time in every case. So I can do an alpha and then maybe like a lambda x dot fx, or maybe I don't know, like x dot 1 or x dot 2, and I can also do x dot 3, Okay, maybe you get the idea. So I can also do it like this. So in Agda this would be eta contracted to just x, or an alternative solution to first query the alpha and then perform an eta contraction. Okay, maybe there is a better example, like if I have an x and I can do an f of x.1, x.2, right? So I think this is probably a better example, because this requires some fairly expensive machinery to do with the previous solution, but it's very simple with the new solution. Maybe I want to unify this with f. Okay, so here I'm unifying lambda x dot f x.1 x.2 with a. So I'm just introducing x as a new bound variable to this problem. So I have f x.1 x.2 equals ax. And now I have another unification problem. So this unification problem can be solved again using the same method. So now I have to unify x.1 with a prime, and I have to unify x.2. So if I unify x.1, okay, sorry, this does not yet work. This example needs a bit more stuff. Sorry, I haven't yet talked about, but okay, maybe we can just do like a. It also works, but it needs a bit more machinery, and we will get to it in some time. So this also works, but because here I have to do xy unified with a, but then there is the usual unification rule for sigma types. So like how can we decide eta conversion for sigmas in unification? And then the way is that if we have a pair constructor on one side and a neutral expression on the other side, then we just try to unify the projections. So here at first I try to unify x, and then this has this and then I try to unify this, and then I get this, and now I have to do a merge. But obviously in an implementation I wouldn't explicitly merge these substitutions, but I would only just use some mutable data structure to update it with all of these individual mappings. But after we do the merging, it becomes this. And now we get this substitution, so we can do the solution. So it becomes lambda a dot, and if we apply this substitution to the right hand side, then it becomes a dot 1. So this is an example for doing for solving this problem. So solution didn't create any new methods, any new types or methods, and didn't use currying. So the old algorithm would use currying in this case. Okay, so this is not an eta conversion example, but this is currying example. I'm sorry, I'm a bit confused. I'm a bit confused. The eta conversion example would be like I just skip it because it's quite obvious. If I have an alpha and then I do and x.1, x.2. Will it even work? I'm not sure. So then I have to unify x.1, x.2 with alpha. No, it wouldn't yet work. It also needs the extra machinery. Okay, but this currying example works in a very efficient way. Okay, and now do a kind of another currying example, but now for handling projections. So alpha x.1 equals x.1. I think this is the simplest example. So the previous unification algorithm, what it would do here is to, so if we have this bound variable in gamma, we have x a times b. So then it would curry this x in the local context. So gamma would become some gamma prime, and instead of x we would have an x1 and an x2. So it would solve this problem by currying. And in my algorithm, what would happen is that I want to unify x.1 with a. And then I also have to use currying. So use currying here, but in general, the only thing that I have to do, is basically eta expansion, and the eta expansion is the most efficient operation. So the eta expansion is kind of like this example is when we can use the axiom of choice in the return type. So it's very efficient. You can look at the elaboration to implementation. So it is pretty much the easiest thing, and it is also the most efficient thing which we can do when we want to extend unification to sigmas. And the nice thing about my algorithm is that the only thing that I have to additionally implement is this eta expansion operation for metals, but also for local variables. And it is possible to implement this expansion in a way which does not have to construct the actual isomorphisms. So the way it works is that when we are doing this this unification of everything in the spine, then we do not only return a partial substitution as a result, but we also return a substitution which is the expanding substitution for gamma. So we don't only return some p sub which goes from delta to gamma. So we don't only return an sp minus 1, but also kind of an expanding substitution. Let's call it maybe exp, which is a total substitution going from gamma prime to gamma, and then actually this inverse substitution, it goes into gamma prime. So then after we finish processing the spine, we can compose this sp minus 1 together with the exp, and that's going to be our actual partial substitution which we use to process the right hand side. So this goes from gamma prime to gamma, and this goes from delta to gamma prime. So how does that work out? No, sorry. So So we have one which goes from gamma prime to gamma. Just one moment. So the original SP went from gamma to delta. SP minus 1 should be partial from delta to gamma. But now I also want to have an expansion which goes from right, which goes from gamma prime to then maybe this should go into gamma prime, maybe. Oh yeah, right. So so I was correct before. So this partial substitution, it goes from the eta expanded local scope to delta. And after we finish, then we can just do this composition. So go from delta to, yeah, we can do SP minus 1, which is a partial substitution from delta to gamma, and then it becomes well typed to do an array-just X composed with SP minus 1. Okay, but let's continue this example. So here we have, we want to perform this unification. So what we are doing is, so in the actual implementation, we are maintaining two mutable substitutions at the same time. So when we are doing this traversal of the spine, so we maintain the SP minus 1 and also the X substitution. And we are just doing mutable updates whenever there is a need to do it. Okay, and in this case, so if we are continuing this problem, then what happens is that we just eta expand. So add X X1 X2 to exp. Okay. And then this problem becomes x1a, and then we can just solve it as usual. So we are just adding x1a to sp minus 1. Okay, and then what is the overall result of performing this inversion? So now x has this, so the overall result will be x sp minus 1, but this is just this composed with this, which is just this. Right, so the composition of substitution operates kind of element-wise. So then we apply this substitution to every mapping, to every right-hand side of a mapping in the first substitution. So we are applying this substitution to this, but here we only have x1. So then the result becomes this, and then we can do an array just x composed with sp minus 1, and then it becomes a x2. Sorry, it becomes, so because the array just was x1, and now we want to replace x with this pair, but then we immediately do the first projection, so it becomes a, and then the overall solution becomes lambda a dot a. Okay, so here what we can do in this case is to do a direct solution without computing any type, any extra type. And we can also, because we do not have to do this. So we have to do this eta expansion substitution when we are updating this expansion substitution, but it can be done very efficiently if you have the point levels. So this kind of like a nice representation of this expanding substitution, it could be also done in Agda, or like in this kind of solution. It would be an available optimization there. I don't think it works that way in Agda, but even if we have that optimization in the previous solution, we still have that here we do not have to compute any extra type, and previously we've also seen that we do not have to create any new type and meta for solving this problem. So we are just getting much more direct solutions without extra noise in the meta context. And if you look at this, then it's a bit like a pattern unification, but recursively. Because if we want to solve this problem, then we want to solve recursively a bunch of subproblems. And the subproblems also use the same principle of pattern unification. And whenever we have a pattern anywhere, so I can have a pattern in the top level, or I can have a pattern in a recursive subproblem of this inversion, then I can use pattern unification. If I do not have a pattern, then I can use the eta expansion. But I do not have to use explicitly a currying or an axiom of choice, or even a flipping. So I do not have to use these explicit isomorphisms anywhere, because just the way of recursing into something in a spine, it already takes care of all of these issues. So I can give, for example, an example for flipping, which is a completely new feature. So if I do an alpha lambda xy f yx, and I want to unify this with f, okay, then I unify with a, which means that I have to unify fyx with axy, but this is just, it's already a pattern problem, so I can return the substitution which maps f to lambda xy to a. Sorry, this is yx here. So this is yx here, but it's xy on the other side. So it becomes a lambda yx dot a xy, and then the solution becomes alpha. Alpha is just lambda f dot flip f in a sense. Okay, and here the flipping is implicit, because we are reusing the usual unification decomposition in order to do this inversion on the spine. And the usual unification decomposition just goes under these lambdas, and then here if we get the pattern, then we can solve it, and then the solving takes care of this flipping as well. Okay, so let's do some more kind of more involved example. Maybe we can just copy and paste a previous example with maybe some axiom of choice. Okay, maybe let's try to do this axiom of choice in local context. Okay, and now let's do. Okay, let's do this problem. Then it becomes fx.1. Okay, and now I have to do an eta expansion of f. So eta expand f, And this eta expansion of f can be done in a purely syntax-directed way. So I can just simply look at this term, and I can just perform an expansion whenever I see a projection. So this also does not require computing types. Okay, and then what is the eta expansion of f? It's the same as before. So we get an f prime, or we get an f1 which goes from a to b, and then we get an f2 which goes from a to c, and there is this kind of the running expansion substitution. So we are adding to x, and then the problem becomes f1 x a, and then sorry, here we also need to have an ax, and then f1 becomes lambda x a, f1 becomes lambda x ax. Okay, and now for like the result would be the composition of the expanding substitution and the partial inverse. So I have to do an x composed with sp1, so that's this composed with this, which is just f mapped to lambda x dot, and then here f1 is lambda x ax, so this becomes ax f2 x, and what was the right hand side? The right hand side was just simply bool. But here I could have also said that maybe the right hand side is lambda x dot fx dot 1, and then maybe it's a pair of a function and a boolean, and here you can see that in this unification problem there is a quite complicated relation. I mean, in the sense that we see that we have the same thing in the spine and exactly the same thing in the right hand side. So there should be just a direct mapping in the solution from this to this. Okay, so, but now I can just take the right hand side and then use this substitution on it. Yeah, okay, it's good. Right, because if I'm performing this substitution, then this becomes lambda x dot ax. And I'm also doing the computation. And then I can solve alpha as lambda a, so we always have this lambda a. And then this is the solution. Okay, so I'm not sure how clear this was. I think we are finished with this topic. Probably there isn't enough time to talk about anything else. But I hope that kind of you get something about how this algorithm works. So essentially what's happening is that when I want to invert a spine, then I'm using unification recursively, and then I get potentially more patterns, and then I I have to do more recursive inversion and unification. So it's kind of recursive mutual implementation of inversion and unification. And the reason that it's so efficient and so powerful compared to the previous problems is because the usual unification already handles the eta for sigma. So usual unification already handles eta for sigma and pi efficiently, and also in a purely syntax directed way. So the thing which I get back from this inversion operation already takes into account the eta for sigma and pi. And that's why I do not have to use explicitly all of these given isomorphisms which shuffle the sigmas around or flip the arguments of a function. So because here we have a very nice solution in usual unification, then we can just use this to enhance spine inversion by using this unification in a recursive and mutual way. So any questions or comments? About this? No comments, no questions. Yeah. So I will try to do an implementation, and then I think, I mean, in the elaboration zoo. So if this works, then this should be in the elaboration zoo, and the other solution should be just drawn out. So, I mean, my aspiration is to only have the correct solutions in elaboration zoo. And because I was not super involved in sigma unification before, I haven't looked very closely at this problem. I was not aware of this solution last week, but now I think this is the right solution. So do you think an implementation will be much simpler than the other stuff? Yes, of course. Yes, much simpler. Maybe conceptually not simpler, because in the other solution we just say, oh, we just have this isomorphism, then just use all of them. But then the flipping does not work because the flipping is not a directed isomorphism. So I should also mention it. The flipping is not a kind of a directed iso. So there is no canonical direction to use flipping. Yeah. So that's why the previous solution was not able to do unification modulo flipping. But yes, in general, I think this is much simpler than the other solution. But even if it was more complicated, then because it is so much more efficient, I would still think that it's worthwhile to consider it.
So yeah, I think it also seems more principled and less hackish than the previous solution.
Yeah, and now what I haven't talked about, and I'm not sure when I can write it down or talk about it. Maybe there should be a voting. So should I talk about like formalization of unification in CWFs, and then like these have this kind of topics, like we have I can just give a table of contents. So we have substitutions, renamings, embeddings, epi, mono, iso, factorizations, and then we have like cospans. I mean cospans in this category of context, and pushouts of embeddings, and then basically a partial substitution is just defined to be a cospan, and then the composition is defined to be a pushout, and then we have kind of definedness of psub, and then we get the poset enriched category, and then we can implement this inversion algorithm. And so we also get the partial inverses of terms, and then we can use all of this formalism to implement the basic version of this kind of nice recursive pattern unification. So it's not yet finished, but I think there are many interesting kind of categorical definitions here involved. But I'm not sure how interested. So here maybe like previously the topic was always about implementation in a more concrete way. And I think it's perfectly acceptable if one just tries to look at an elaboration Zoe implementation of this unification algorithm and just understand it. And this is kind of just an extra. It's not completely necessary.
I would be interested, but not. I mean, the detail, categorical details are not that much that interesting. I think it's more like the whole well-typedness and how you can view this unification as an algebraic, how you can describe unification in an algebraic way, and that's interesting.
Yeah, I mean this is the description.
It's always untyped, and yeah. So that's the part that I'm interested in.
I mean, I think we need all of these to formalize. So I mean, in the elaborations, I have
that's good.
I have a small node, but only for the simple pattern unification. So in this 0, 3 holes, I have this pattern unification.txt, and this is not very long, and this is which I already worked out, and here I just have a bunch of definitions like epimorphisms, renaming, properties, embeddings, factorization, strengthening, and then this is just kind of a sketch of a proof that the pattern unification is unique and decidable. But this only works for the simple naive pattern unification. And if I actually want to formalize the algorithm for performing the inversion in a fully formal way, then I already need to have this notion of partial substitution here. Or maybe I can talk about it in a type theory seminar, right?
Yeah, that's also good. Yeah, I don't mind.
And then we can also record it, and if people are interested in it in this seminar, then they can watch it.
Mm-hmm. Yeah, that's a good idea. So not the next one, but maybe the one after the next.
Next one is
Gregory.
It's Gregory. Okay, so that's it. Balázs says it's not sure a good idea to throw out already existing implementations. It can be useful for pedagogical reasons. I partially agree. I think it's possible to simplify the existing implementation so that it only does this eta expansion, because the eta expansion is reused in the nice solution. So there could be an intermediate implementation which only has the eta expansion but not this recursive pattern unification. But I don't think it's a good idea to keep wrong solutions around. I think that's pretty much the way that a bunch of wrong implementations come to exist in reality, is that there are tutorials using the wrong implementations and then people copy it.
I mean, you should have a big warning on the top that this is a failed direction. But to compare how much more complicated the fair one is, I think that's, so knowing the existence of the fair directions, I think is a good idea. But
yeah, but I think that I can just link to the unification paper. If you want, or I can link to mondjuk Agda source code is a bit heavy, but I can link to the paper, definitely.
Yeah, but I think it's useful to have it in exactly the same format as your formalization, so that the people who are already familiar with your style of writing stuff, they see how the failed attempt would look like in your style.
Yeah, I mean what I talked about here, like here I just summarized the other solution. I can just keep this as around as part of the explanation.
Yeah.
So I think in education it's much more impressive to see the good solution after seeing the less good solution and see how much easier the good one is than directly just only the good one. Of course, it's a trade-off because that takes more time. But,
Okay, so time's over, so maybe we can finish. And I'm not sure what will be next week. Probably I can also prepare something for next week. I promised some glued evaluation, like more elaboration with glued elaboration, but this week I haven't worked on that because this was the problem that I focused on. And I think it was very fruitful, but next week maybe I can try to do some glued elaboration. Okay, then I stop the recording.